we are going to continue our discussion on equilibrium constants, which means we are moving forward with chapter 15. To give you an idea of our timeline moving forward, this is the end of the third chapter of the semester, which means that we have a test next week, Thursday. You can put it in your calendars now. Thursday double period. First half will be multiple choice, second half will be your short answer. And yes, we will spend some time reviewing next week. For now, we're talking equilibrium constants. And last we left off, we just kind of introduced what an equilibrium constant was, how to write equilibrium constant expressions, and how to manipulate equilibrium constants from Kp to Kc and vice versa, as well as how to, say, flip an equilibrium constant so that we can get the reverse equilibrium constant if we would like to. From there, we discussed just how solids and liquids impact. This is kind of something that you guys already know, but solids and liquids do not impact our expressions. However, they do still matter. A lot of times what we do is, in order to convert a solid or a liquid, we can multiply by a density to get into a molar mass, and so on and so forth, right? So when it comes to solids and liquids, they are not present in our equilibrium constant expressions. It doesn't mean that they do not impact our reactions altogether. Please remember that when we are dealing with these types of expressions, these equilibrium constant expressions, they are constant for only whatever temperature we're analyzing at the time. Okay? So remember that solids, liquids do not actually impact our equilibrium expressions. Yes?
Sorry to interrupt. Can I sharpen my pencil?
Yeah, go for it. Just a reminder, solids and liquids, pure things, do not have any impact on your equilibrium expression. Okay. When we talk about our gases versus our solids, if we wrote an equilibrium expression for this particular reaction, there would only be one substance in our equilibrium expression, and that would, of course, be the gas, CO2. As long as some of the other two solids still remain, you're going to see that CO2 will also remain the same, right? So once we reach that equilibrium, just don't forget the principle behind equilibrium, right? It says that once we reach that equilibrium, as long as we don't agitate the system, if we don't add anything else or we don't subtract anything from our system, we don't change the pressure, we don't change the temperature, those concentrations should stay the same, okay? And that does go for the solids as well. We don't measure those concentrations, we don't measure those masses, but they do still have to follow the principles of our equilibrium, okay? From there, we have to talk about how to actually do math with equilibrium constants. And we're going to do a series of practice problems. There's a bunch that we're going to do together. But in lecture, we're just going to kind of introduce the basics, okay? Here we have a problem. We're given information about this problem. One of the things we're given is an expression, okay? If we wanted to, could we write an equilibrium constant expression for that particular reaction? Hopefully at this point you feel comfortable doing that. You take the products, you divide by the reactants, you raise them to their coefficients, you ignore solids and liquids, okay? From there, we can do a couple of things. The first is going to be to introduce what we call ice tables. Ice tables take an initial situation to equilibrium, initial change equilibrium. We're given information about the initial concentrations of this particular situation. We're told that at equilibrium, the concentration of one of the things is going to be this number, and our goal is to calculate what K is. Now, for any and all equilibrium situations, the very first thing you should be able to do is to write an expression. The very first thing you should be able to do. From there, we can also then create what we call an ice table. Now, sometimes an ice table is really useful. Sometimes we may not actually need to do anything with the ice table. We're going to use them for every single problem regardless because it's a consistency thing. Right? Consistency with you guys is going to be key, especially since we like to do things in a procedural manner. Any of these different things that we're going to do is going to be a procedural-based idea. Okay? One of the things to remember about concentrations is they are typically given in moles per liter. A lot of these different problems that we work with may give you moles of each individual thing and tell you it's in a 2-liter flask. So you may actually have to do a calculation to figure out what a concentration is. You may be asked to calculate pressures. And to remember how to calculate pressures, you're going to have to use the ideal gas law at some point, okay? So some of the very different pieces of information you'll be required to do, not necessarily for this problem, but in general. In this particular reaction, what is our equilibrium expression going to look like? Product, right? Remember that gases matter. We're going to take that and we're going to raise it to the power of 2. We're going to divide by the only thing present on the reactant side that has the gas or the aqueous symbol. Okay? Our goal is Kc. When we write out our reaction, this is where we're actually going to be able to write out what we call an ice table. Pretty sure. There we go. Okay? Again, I, C, E. I stands for initial, C is change, E is what happens at equilibrium. If we want to get a K value, what numbers do we have to plug in? The initial, the change, or the equilibrium values? What do you think? K expressions are equilibrium constants, aren't they? So what kinds of concentrations should be in there? Equilibrium concentrations. Initial concentrations have no business being in a K expression. I don't know why it gave you I. I didn't count. I guess it's better. We were given the equilibrium concentration here. Using ice tables, the change part is the part that's usually the mystery. So of course, to indicate a mystery, a lot of times what we use is an X value. In this particular case, we know that this thing went from 0 to 1.87 times 10 to the negative third. So we know that this is what was created. Since our reactants are the things that actually have to produce this, and it's a 1-to-1 reaction on the left side, we know that each thing had to give off half of whatever was created on the right. Okay? And we're going to learn a method for actually doing this that doesn't involve just assuming this particular thing. But in our particular case for this problem, the way it's designed is beautiful. Because you have a 1-to-1 thing that makes a 2 thing, right? And they're going to equally be used up to do this. From there, we just do the math to figure out what these equilibrium concentrations are, given as this. Now we have equilibrium concentrations. Can we calculate a K? Heck yes, we can. We can plug in our equilibrium numbers to calculate what K is. We have not done this yet. So far, all we've done is write out K expressions, manipulate K values. We have not actually calculated Ks. Do K values have units?
Not really.
They do not. K does not have units. Can K be small?
Yes.
Can K be large?
Yes.
Can K be negative? Always positive. Okay. So let's calculate this number. The beauty of this one is that it's already done for us. Yes, this is subtraction. Change parts of your tables are always going to be either subtraction or addition. Remember that when we do reactions, we assume we start with the reactants and we end with the products, which means reactants get used up, so they decrease in concentrations. Products get created, so they increase in concentrations. So anytime you see a reaction, you're going to put the pluses on the right side and the negatives on the left side. All right, so in calculating this, they included I. Should they have included I?
No.
Heck no. According to their original reaction, I was a solid. So is that right?
No.
That is wrong. You should only be doing this one. Someone plug it in and tell me what you get. This one's always wrong. Don't worry, we're going to do a lot of those. We're going to do a lot of these. I mean, all day. Today and tomorrow. Get excited. Everyone agree? Yeah.
Why is the what value is it? The ethyl value? Why is it so?
The original reaction had a 2 in front, remember? So when you write the
okay.
expressions, the coefficients become the powers.
Iodine squared.
What'd you say?
Iodine squared.
Yeah, I was gonna say I didn't do that.
What'd you get?
I don't think this one's right either, but I'm redoing it. I got 0.0498.
Doesn't sound wrong. It's a big exponent on the bottom. Did you get that? Kinda, sorta, close?
Yeah.
Please just remember when you do things in your calculators, which if you don't have your calculator out, get it out now, that you use parentheses to the best of your ability. When plugging this into your calculator, I would put parentheses around that after you square it.
I got 0.0537. Yeah. Yeah.
Sounds good? Sounds good to me. All right. So, at this point, we have a way of analyzing what happens at equilibrium. If we want to compare what is supposed to happen at equilibrium with what is happening outside of equilibrium, we are going to introduce this idea of Q, the reaction quotient. What this says is if we know if we know concentrations of our reactants and products outside of equilibrium, so before it reaches equilibrium, we can use a Q value, the same expression as K, mind you, to determine which direction the equilibrium must move to get to equilibrium. Which direction does this reaction need to move given the concentrations that we started with to get to equilibrium? We would say it needs to move to the right or it needs to move to the left. So Q is an expression of what should happen if it wants to get to equilibrium. For Q, the expression will be the same as K. So you will plug numbers in to a K expression to compare Q to what K should be. This means you must already have a K. Okay? It means you must already have a K value to compare. You're going to substitute initial concentrations into the equilibrium expression that looks just like the K1, and you're going to compare Q to what it should be. Does that make sense? It's an odd idea, but in doing this, we can determine where our reaction needs to go to get to equilibrium. If our Q value is much smaller than K, what that means is that the reaction needs to form products to get to equilibrium. If our Q value is much larger than K, the opposite needs to happen. Our reaction needs to form reactants in order to get to equilibrium. If our Q equals our K, it means that our reaction's at equilibrium. And nothing needs to shift. So Q is a comparison tool. We're going to calculate Q the same way we calculate K, except we don't know if the reaction is at equilibrium or not. We want to determine if it's at equilibrium, and if it's not at equilibrium, how is it going to get there? Yes?
But if it's in like the equilibrium part of like our table, does that mean that Q is always going to equal K?
So you won't always know that. What we're saying is, for Q expressions, this is different than this altogether, right? This is a table that we're going to use knowing initial and equilibrium and trying to get from one to the other. What we're saying about Q is, you may be told, all right, the concentration of HI is 0.47 molar. The concentration of H2 is 0.35 molar. What needs to happen? Okay, so here's the question. Where is this reaction? Is it at equilibrium? Does it need to shift to get to equilibrium? If it needs to shift to get to equilibrium, which direction? Does it need to form more products? Does it need to form more reactants? So in order to figure it out, we have a K value. We just calculated it was like 0.05, right? And some other numbers. Okay, so in order to figure this out, we're going to take our values. We're going to plug them into the K expression. So we're going to take our 0.47 squared. We're going to divide it by 0.35, and we're going to get a Q value. So someone do that in their calculator. Ma'am? You still screw the top number because that's the expression, right? We don't deviate from the expression.
0.6311.
Okay? So in this case, our Q is greater than our K. At these concentrations, this reaction is not at equilibrium. We just proved that, right? We also just said that since Q is greater than K, that our reaction needs to do what? It needs to form more reactants, aka it needs to move itself to the left in order to get to equilibrium. So again, this is more of an equilibrium indicator. Does that make sense? Comparison tool is what I like to call it. Okay. If Q is greater than K, if Q is less than K, if Q is equal to K, get that written in your notes, please and thank you. The last thing we have to cover in this particular chapter is Le Chatelier's principle. Okay? This is Le Chatelier's principle word for word. What it says is that if our system is at equilibrium, aka it's already going nowhere, right? We've already got the rate of the forward reaction equal to the rate of the reverse reaction. The concentrations of everything are steady, okay? Le Chatelier says that if you disturb that equilibrium by changing temperature, concentration of something, or the pressure of something, that the equilibrium will shift to get back to equilibrium. You may have new equilibrium concentrations, but eventually your system will equilibrate again. Equilibrium reactions react to disturbance to get back to equilibrium. And they will do the opposite of whatever happened. So if you add more products, right, then the equilibrium will shift to get rid of those products to make more reactants. Le Chatelier predicts that if you do something to the reaction when it's at equilibrium, you will change equilibrium concentration values. Pressures will go up to a new number or down to a new number. Concentrations will go up to a new number or down to a new number, etc. Okay. And here's where we talk yet again about the Haber process, the Born-Haber cycle that produces ammonia. Okay? We've talked about it before. We've kind of introduced the reaction. We discussed it a little bit. We use the Haber process because it's very useful in agricultural applications. We talk about it a lot because, again, it's a really common and very simple reaction to discuss. In this particular case, we're talking about the Born-Haber cycle and why it has anything to do with equilibrium. So it's not just a forward reaction, it's one that is actually reversible. The beauty of it is that we can study it very easily. It's hydrogen gas and nitrogen gas makes something else, right? And hydrogen and nitrogen are pretty abundant in our atmosphere and easy to get. So we use it just to study equilibrium. It has no significance other than a beautiful reaction for us to watch and to measure information about, okay? Good model reaction, if you will. The Born-Haber cycle is one thing that we can use to actually demonstrate what happens with Le Chatelier's principle. If we add more hydrogen gas, we're going to see that the concentration of NH3 has to shift upwards. If we add more ammonia, then we're going to see that the whole reaction has to shift towards the left and will create more hydrogen and nitrogen. Okay? Again, a beautiful model reaction to study Le Chatelier's principle. Okay? In this particular case, we've designed very, very complex systems to watch the individual products and reactants and how they are affected when we add one, subtract one, change the temperature, add more pressure, that kind of thing. Okay? From there, we just want to make sure we understand. In chapter 14, we talked about the effect of temperature, right? Temperature changes things. If we change the temperature of a system, things change, all right? How much of something gets produced is going to change. How quickly the reaction happens is going to change. When it comes down to it, temperature is a really, really big factor for us to pay attention to. In this chapter, for the most part, we deal with constant temperature situations. So keep that in mind. But fair game question is, how will temperature affect an equilibrium situation? Okay. In this particular example, we have an equilibrium reaction shown. As you add heat, the reaction shifts to the right to increase more product. If you remove heat or you make it colder, the reaction shifts more to the left. And that is this particular reaction. Okay. In general, if you speed things up, you're going to produce more product. If you slow things down, you're not going to produce as much product, which means you're going to have extra reactants laying around. So that is the typical effect of temperature. Topic in this chapter on catalysts. You've seen catalysts before. We know what catalysts do to the rate of a reaction. They reduce the amount of energy needed to get the reaction to move forward. They speed up a reaction by reducing that activation energy requirement. Okay? Because catalysts increase rates, what do you think their effect on equilibrium is? I would say that since equilibrium reactions are things where we say that the rate of something in the forward direction is equal to the rate of something in the reverse direction, if we speed them both up, we're going to see greater numbers in general. We're going to see higher concentrations, we're going to see higher reactant concentrations, and things of that nature. But in the end, when it comes to a catalyst, equilibrium is going to not shift at all. We're going to see things happen faster, sure, but do we care about speed in this chapter at all? No, because the principle of equilibrium says it doesn't matter how fast it's moving, just that however fast it is moving in one direction is how fast it's moving in the opposite direction. So equilibrium concentrations are not affected by catalysts. They are just impacted as far as the rate is concerned. So how quickly it's going to happen is still going to be a factor. That is it for that. All right, so we're going to switch over to practice problems. In your module for today, underneath today's daily cue, there is something labeled 15.5 through 7 practice. We're going to do 6 problems together. There are a lot of other problems for you to do on your own, and you'll have time in class today and tomorrow to do them. But today, we do those first 6. We're going to start with number 1. You have access to them. You're welcome to look at them in front of you. Can't see. Yes, sir.
So we only have to turn the U-turn portion of the problem?
Yes, you do not have to turn in this portion of things. That is correct. All right. I will remind you that when it comes to equilibrium problems, the first thing you're going to do is write an equilibrium expression. So we're given information about what's happening in this particular flask. We're told the value of the equilibrium constant K. We're given an overall reaction. So I'm going to start by writing a K expression. We're not given states of matter in this particular problem, so we're going to assume that they all matter. Nothing. Nobody. Great. Yeah. I tried. My attempted humor for you is pretty much all you get today. We are also told K as a value. Next thing to do is to write the equation and make an ice table. I like to make my ice tables underneath the equations that I write. And you'll see why. And then we are going to look for information to add to the ice table. We're told that we have 1 mole of H2 and 2 moles of I2. Do you think that those are initial or final concentrations? Probably initial concentrations. It says that the flask is charged with, meaning something is added to. And then it's allowed to come to equilibrium. The second clue that this is not at equilibrium is that this says, what is the equilibrium concentration of everything at equilibrium? Okay? So first thing I'm going to do is I'm going to write in concentrations here into my initial area. If I'm not given a concentration, it is 0. If I'm not given an initial concentration, you assume it is 0. Next thing is, I was told 1 mole, which is not a concentration, but I was also told that this flask is 1 liter. So if I want to calculate the concentration, I'm going to do moles per liter, right? 1 mole over 1 liter is just 1 molar. 2 moles over 1 liter is still just 2 molar. All right, now, were we given any information about equilibrium at all? I mean, we were told the K expression, right? We have a K value. Problem is, we don't know what any of the equilibrium concentrations are, and here's where we're going to introduce that method. We know things are going to change on this side, right? And they're going to go down. They're going to go down by some unknown number. On the right side, they're going to go up by double that. Why do I know double that? Because the coefficient says so. So the 2 in front of the x comes from the coefficient. Okay? Then I just drop everything down. Zero plus 2x is just 2x, right? Now I have equilibrium concentrations. Now I plug them into an expression. If you don't see it already, yep, you're solving a quadratic today. Oh, yeah. It's kind of a problem. Do you need a charger for your calculator?
Yeah, if you have one.
I do. Okay, so what should you do to the number, what should you do to the two expressions on the bottom of the fraction? Yes, you should FOIL them. Oh. That's what I got when I FOILed it. So this whole expression, ooh, 2x squared becomes what?
4x squared.
Thank you. What do I do next? How do I get this into a solvable quadratic formula? We gotta get everything onto one side, right? Doesn't the quadratic formula say ax squared plus bx plus c equals 0?
Yeah.
So we gotta get 0 on one side. So I'm gonna multiply the stuff on the bottom of my fraction over. I like to call this math class with Mrs. Shupp, Mrs. Mole, whatever you like to call me. I think it's bad this year, wait till physics. We do math together all the time. We do algebra together all the time, though. Algebra's easy. It is. I mean, at this point, if you don't have a quadratic solver on your calculator, I highly recommend you get a quadratic solver on your calculator. Oh, it's a program that exists. Yeah, it exists.
Where? Can I make that a module?
Walk up to Mrs. Bell and ask her for a calculator and transfer the data over. She'll give it to you.
C, is that right? B squared?
I don't know.
Yeah. Yeah. I know it because Pop Goes the Weasel.
What?
I had to memorize quadratic formula when I was in high school, and they made us memorize it by singing it to the tune of Pop Goes the Weasel.
Are you serious?
Oh, it's a good time.
Can you sing it for us?
You want me to? Sure. Ready? Negative b plus or minus the square root b squared minus 4ac all over 2a. Guys, they used to torture us just like we torture you. All right, so here's this expression. What do I do next? I mean, yes, you could subtract 4x squared, but I would probably distribute this first into this particular lovely expression, and then subtract 4x squared so that you know where that's going to end up. You're fine. If you do it all correctly. You get this. Then you solve for numbers. AKA, what does x equal? Yes, sir? Does everybody remember where you get the a, the b, and the c for the quadratic formula? Okay. Does everybody also remember that the quadratic formula will give you 2 answers for x? Okay. The 2 answers you get for this x. This is what I like to call the rare situation where both values are positive numbers. So you have to use some number sense. If we look back at our original initial concentrations, the lowest one we have is a 1. Can we get a negative concentration? Please say no.
No.
We're talking matter here. You can't have negative matter, right? So that being said, which of those two numbers doesn't make sense? The first one. This guy doesn't make sense because our smallest concentration is 1. So 0.935 must be our x value. A lot of times when you solve quadratics in this particular type of a problem, in our equilibrium problems, you'll get a positive number and a negative number, and then it's really easy to figure it out. Yes? 50.5 x squared minus 4x squared. Yeah. So the 2.32 does not make sense because this concentration is smaller than that. You can't have a negative concentration. Yes?
Wouldn't it not make sense because you can't have an x value bigger than your concentration?
That too. That's what we're saying is like your x value has to be smaller than your smallest concentration. Both of them are technically smaller than 2. But what we're saying, or smaller than 2.3. What we're saying is the one that makes sense is the one that's going to leave you with something left over. Or 0. 0 is an option. All right, so now let's actually figure out what our equilibrium concentrations are by plugging in x. So you figured out what that x change is, but you're not done. The next thing to do is actually to figure out your equilibrium values by doing the math here. Can I erase my quadratic? What do we get? Let's do this one. Thank you. What about this one? What about this one? Okay, so now we have equilibrium concentrations. Are we done?
Hopefully.
It says what are the equilibrium concentrations of all of these molecules at equilibrium. So we're good.
Oh my god.
That's number 1.
Is it that I...
Well, we are done because the goal was equilibrium concentration. Just don't forget as you're solving these problems to look back once in a while at the original goal, all right? Otherwise, you'll just keep on going. It doesn't make a lot of sense, but you'll keep on going. Oh, I mean, you could plug it all back in. If you wanted to, could you check your work by plugging it all back into K to figure out what K comes out to be? Yes, you could, but... All right, let's move on to the second one. Again, we start by writing a K expression. We're given an equation. Let's just go ahead and write it. From there, we can plug in information we are given. So reading the problem, we are told the value of K at equilibrium at a certain temperature. You'll see that you're always given a temperature. Sometimes you might have to use it. Sometimes it's just there to tell you it's there. In this particular reaction, we're told that K is 0.078. All right. Next thing to do is to rewrite the equation and make your ice table. Again, we will get to problems where we won't really use the ice table the way we're introducing. But for now, let's use them every time. Because you don't know the difference quite yet. You will. All right. So we're given information about an equilibrium mixture. The concentrations of two things are these. What is the pressure of Cl2 in the equilibrium mixture? In order to get a pressure, we need that. Anytime you're asked about pressures in these equations, we're using the ideal gas law every time. Okay? From there, we need to know what the concentration of Cl2 is in the mixture, or we need to know Moles over volume is concentration, right? If we can find concentration of this, Cl2, we just have to multiply by RT, and then we'll get pressure. Okay, so this is the goal of this particular reaction. Okay, let's fill in what we know. We weren't given initial anything, right? We were given concentrations and, or we were given molar amounts? No, yeah, we were given molar amounts of SO2Cl2 at equilibrium and SO2 at equilibrium. We don't know what Cl2 is. Anytime we don't know what something is, just put an X in. You're making an algebraic equation. What do we do next? What do you think?
Solve for X.
Oh, we absolutely have to solve for X, but we got to put all those numbers in an expression first. What expression should we use? The K expression! We're going to plug in numbers in this one. X. You solve for X? Yes.
0.162.
Oh, that's fast. I got a question.
I didn't even write it down.
It's all good. Sorry, we're not done. Because that's not a pressure. The question is for a pressure. Huh? Yes, you just multiply by RT. Please don't forget that when we do the ideal gas law, what unit should your temperature be in? Kelvin. You were given a temperature in Celsius. Convert it, please.
Yeah, I suppose so.
There is a 0.15, but most of the time we just ignore that the 0.15 exists because everyone forgets. If I say, hey, remember to add 273, we struggle to remember 273. If I say, hey, add 273.15, you're like, what? So you know to keep things simple and not lose my mind. This is the next one we're doing. N over V means concentration. Do we have a concentration in moles per liter? We do. So we're going to take that 0.162. We're going to multiply by R. And then by T. What do we get for our pressure? 4.96 what?
Atmosphere.
Thank you. It's a 4. That was number 2.
I don't understand.
We're starting them all the exact same way, but they all kind of do a different thing towards the end. I'm aware.
In the moment, I like understand what you're doing, but then in retrospect, I have no idea what just happened.
You need to make sure you're writing stuff down.
Well, I am.
Thank you.
I'm gonna leave this up in case we need pressures again.
Yeah.
Can I erase?
Yeah.
I heard no.
Yeah, go for it.
I just thought louder
Okay, nice.
All right, number 3. You can set up the very beginning of it without me. Let's go.
I'm doing it.
Get to it. Number 3, get it set up. You can write the equation. You can write the ice table. Here you're given moles and liters, and you're actually going to have to divide them, so figure out what the concentrations are in moles per liter. Get me an expression for K. This one's actually pretty straightforward. Just calculate K as you plug numbers in.
I still don't understand why immigration or customs has anything to do with this. Why immigration or customs has anything to do with this, or the enforcement of this. Think about ICE.
Way to make chemistry political, I really
Does that mean, isn't the initial or the
ICE.
Yeah.
I means initial,
Yes.
E equals
I
equilibrium.
know, well, what we're doing is.
Oh, what does it say?
It says an equilibrium.
I'm so confused.
So
right?
equilibrium mixture means we're at equilibrium. Yes, that's a good question. A lot of this is you have to interpret. Are we at the beginning or are we at the equilibrium? It does! When you calculate concentrations, you do moles over liters. In this case, it's a 2-liter vessel. So take your molar amounts and divide them each by 2 to get your molarities at equilibrium. Someone trying to get in? I got it! Get back to it! Focus! Yes.
I'm a little stuck here.
Okay. You get your K expression first?
Is this a K expression?
No,
it's
that's
not.
just the reaction. So write the K next.
Sure, so,
Okay?
K, do we know K? Is that a given? Yes, it is. 500.
No, K is not given.
Oh, so
You're
it's telling it.
calculating
Gotcha.
K.
All right, so that K would be basically.
I want the expression for
Yes.
K first.
So that would be products.
Good.
Chase, make it up as you go.
Yeah.
So those are the values in moles. You have to divide them by 2 liters. Don't forget to do that. But once you have that, then you have yes. Then you have the equilibrium concentrations, and you plug them in.
So what is it?
Why do I have all 2,000 milliliter one class? Why don't I have a liter one?
Because we were doing the equilibrium stuff. What's up? Yeah.
So you just gotta divide all those things by
Divide by 2
2 and
liters.
then put them into that K value. Okay.
Those are all equilibrium
That much I
concentrations, so
do
you don't even
understand.
have the I or the C. You're just going straight to equilibrium with this problem.
Like 0.0.
All right, remember that I wanted the equilibrium expression. That was the first thing you had to write. Double check that yours is correct and that U squared H squared H2. Right? The next thing you're going to write is the equation, and you're going to make your ICE table. And remember I said sometimes we won't actually have to use parts of the ICE table. This is one of those situations. You are given equilibrium information. It says an equilibrium mixture in a 2-liter vessel. So when I set this problem up, I calculated the concentrations before I put them in my equilibrium table. You could have just put them in your equilibrium table, that's fine. But I want to make sure you understand, if you put 0.17 and 0.302 and 0.0406 in this, you're wrong. Those are not molarities. And our expressions depend on molarities, so concentration values, okay? So for CO, I got 0.0203. Nope, that's wrong. I wrote mine in a different order.
Oh, I was gonna say.
Freshman registration night means I have a whole key and everything today.
Was that last night or tonight?
Last night. Which one?
Well, not a lot of people.
That's H2.
Okay.
Stop it.
I had 2, but
I just want to make sure I didn't want to.
Okay. So I did not have initial concentrations, which means I don't care about changes in this particular problem, but I do have equilibrium values, so I'm going to plug them in. Okay, our goal is K, right? Do we have an expression? Do we have equilibrium concentrations?
Yes.
Plug and chug.
Do you have to square it still?
Of course.
Okay.
Yes, ma'am.
So for like, for the, actually never mind.
Okay.
There's no unit.
Yeah. No unit.
I forget what temperature has to do with this. Like I got the.
This one,
Yeah.
all you need to know about temperature for any of these problems is what it is.
Okay.
Sometimes you won't use it. In this particular case, we just know that K at 500 Kelvin is going to be
So,
whatever we've calculated.
Once we get the K, we're done.
You're good.
Oh my gosh, I did it.
Okay?
I think I did it.
When you're done with this one, you can take a break. You're back at 9 o'clock. You got 6 minutes. I'll put it up on the board here in a second. But it's like 10. 10.47.
I would have rather it like rather than like one of the ones that had like all the steps. So I
Plug them into the K. Put them in here. And find K.
Too much.
Okay.
Okay?
Too much.
Too much.
Thank you.
Okay.
10.47.
CH3OH is on top.
What'd you get?
10.474.
That's what I got.
Yeah, let's go.
Wait, what did you get? Stuck to my.
10.47.
Okay, that's what I got too.
But I got 10.7425.
3 down. 3 to go. Second video.